Hello, welcome to the fifth video in light as a particle. The previous two videos we looked at the photoelectric effect, and in this one we're going to look at X-rays. What are X-rays first and foremost? Well, X-rays are electromagnetic waves of very high frequency and very short wavelength. They're part of the electromagnetic spectrum, and they are in the range of 0.001 nanometers to 10 nanometers. Now, if you look on your electromagnetic spectrum, you can see where they sit. Because of their high frequency and hence high energy, they can penetrate flesh and may cause damage by ionizing atoms they encounter on the way through. When X-rays pass through the body tissue absorbs the energy and the intensity of the beam is reduced. The more dense material absorbs more radiation, and that's why we use them for X-rays, particularly for looking at bones and teeth. If you ever had a broken bone, you would go to the hospital and get an X-ray, because they can actually show up things like that very well. They're not very good for soft flesh, but if you had something, for example, wrong with your intestine, they would give you what's called a barium meal, and that's basically a lot of barium that you swallow or eat, and it goes, and barium being very dense, it goes through your intestines and it gives you a contrast. It's a contrast medium, they call it, and you can actually see the shape of the intestine because of what's inside it, and people can look at it. But that's one of the reasons why MRIs and CAT scans were developed, because looking at soft tissues is important. But X-rays are still used for many uses. If you go to the dentist, you get X-rayed to see if you've got any holes in your teeth. Now, how are they generated? So, if you go to the hospital and you get an X-ray, or you go to the dentist, any X-ray machine would have an apparatus similar to this. Basically, what you have is, and this would be the X-ray tube, and it's an evacuated glass tube with two electrodes, and between the two electrodes they're connected to a very high voltage, 25 kilovolts to 750 kilovolts, which is a very high voltage. So there's a very strong electric field between here and here, and a current is actually put through so electrons are leaving here, they find themselves in an electric field, and they get accelerated, and because the electric field is so strong, they end up getting a very large velocity by the time they get here. Now, this electrode is actually referred to as the anode, and it's rotating, and this is the motor that drives the anode, and it has to rotate, so it actually doesn't, the electrons don't actually burn a hole in it. If it was stationary, this would all get too hot and would very soon vaporize, and so it's rotated, but they still burn out. They have a lifespan that's not particularly long, and this anode is usually tungsten. The other thing is, when you go to have an X-ray, most of the noise that you hear is actually cooling, to keep this whole system cool, because these collisions are producing a lot of heat. Now, the X-rays come out of the anode, and they usually go through a window in the X-ray tube, and then are then used to scan the bone or whatever is being X-rayed. So that's the basic mechanism of most machines, usually tungsten. Now, within that there are two mechanisms that are actually producing X-rays. The first mechanism produces X-rays with a range of frequencies across the X-ray band of the electromagnetic spectrum. And how they're produced is, the electrons, which have a large velocity, are actually slowed down by the target atoms. So they enter the tungsten target and they get slowed down. Now, because the electrons have a massive amount of kinetic energy before they're slowed down, the loss in kinetic energy is converted to electromagnetic radiation, and that corresponds to X-rays in the electromagnetic spectrum. The frequency of the X radiation depends on the amount at which the electron has been slowed. In other words, the amount of braking that has occurred. And X-ray machine operators can actually change the accelerating voltage to work out whether or not they want soft or hard electrons being given off by the tungsten, depending on the need. Now, this sort of X-ray or X-radiation is called Bremsstrahlung, something like that, radiation, which is German for the braking radiation. And this is what's happening. This is a nucleus in the anode, so probably a tungsten atom. The electron comes whizzing in after being accelerated by the electric field. It interacts with the electric field around the nucleus, doesn't hit it, but gets braked and diverted with a new velocity, and the loss in kinetic energy is given off as a photon, which is in the X-ray section of the electromagnetic spectrum. So that's what that says. Deceleration due to the electrostatic repulsion of the atoms in the anode. So it's not just one atom, it can be a whole range of atoms. The decrease in the kinetic energy is given off as a photon. This is the reverse of the photoelectric effect and further evidence of the particle nature of light. The second mechanism, it comes about because of the ionization of the target atoms. So the actual accelerated electrons hit the target atoms and strip off electrons out of the electron shells of the tungsten. So the frequency of the X-rays produced depends on the target atoms. Now this is something we haven't done yet, and we're just about to do it when we do atomic physics. But atoms, we can envisage the electrons around an atom as being in energy levels, and when they sit in these energy levels, if they're knocked out, an electron will drop into those energy levels, and in doing so they will release energy, but only certain amounts of energy that correspond to those energy levels, and every element has its own particular energy levels, and that's why we can only produce certain type of X-rays depending on what the target is. So to produce X-rays of a particular frequency, an electron is knocked out of the inner shell of the target atom by the approaching electron. An outer shell electron then drops into the inner shell space, the gap that's left behind. So this is the ionization, and this is the removal of the ionization by an electron dropping in, losing energy equal to the energy difference between the shells. And that energy is given off as an X-ray or a photon. Hence a series of frequencies that make the characteristic or line spectrum are produced. And we haven't talked about that, and we're not going to really, because that's in the next section. But this is what the spectrum would look like from an X-ray machine. And it's a bit blurry, but this is the braking radiation, basically all these frequencies, or energies, probably a better way of saying it. All these energies of photons are the braking, whereas these spikes are the specific energies that characterize, in this case, tungsten, and the second mechanism of X-ray generation. And here we see a similar one, but here we've got different targets. This target is argon and potassium, and this one's copper and potassium. And so you can see peaks for different elements. And so this is actually one way of using X-rays to identify substances as well, but that's a different story altogether. And here we have it. So this general shape is due to the braking radiation X-rays, and these are the characteristic photon energies of whatever the target is. And then you can convert photon energy into wavelengths or even frequencies. Note that there are only a few characteristic wavelengths, these guys. Their number and position depend on the type of atoms in the target. whereas there are many wavelengths produced by the breaking. Now let's do an example question related to X-rays. An electron is accelerated across a potential difference of 135 kilovolts. So that's the accelerating voltage before it strikes the anode. After the collision, the electron is found to have an energy of this many joules. What is the maximum frequency of the electromagnetic radiation that will be emitted? So we have the kinetic energy of the incoming electron, which equals QV, because that's the accelerating voltage times the charge of an electron. That's how much energy it will gain, 2.16 by 10 to the minus 14 joules. The deflected one has this amount, so if we subtract this from this, we should get the difference, and then if we divide it by Planck's constant, we would actually get the frequency, because E equals HF, which is what this is saying here. So the kinetic energy initial minus the kinetic energy final is the change in energy, or the energy remaining, and that gives us the photon. Now in the next video we're going to look at what's called the Compton momentum equation and its significance in light as a particle. Bye.